Good afternoon, guys. Thank you for joining my talk this afternoon. We'll discuss green computing with computational storage drivers. I'm Changho Choi. I'm a senior director of engineering in Memory Solutions Lab in Samsung, based in San Jose. My colleague, Dr. Kang, is a senior staff engineer in Memory Solutions Lab. I will discuss industry trend that including current data center trend, and another one is a domain-specific architecture to address some potential issues that we have nowadays. After that, we'll discuss computational storage. First, I will discuss what is computational storage, and I will also discuss what computational storage initiatives are ongoing in the industry, especially in the standard groups. After that, my colleague will discuss our value evaluation of computational storage, and then we'll discuss the benefit of computational storage also. We'll wrap up our talk with a summary and call to action. First, let's start from the data center trend. This is a well-cited report. In 2018, almost 20,000 terawatt hours electricity has been used in the world for a whole year. But out of 20,000 terawatt hours, 10% of that electricity is used for information and communication technology sector. Also, out of this, 200 terawatt hours is used in the data center. This 200 terawatt hours electricity usage is almost bigger than one whole country 1 year data, 1 year energy utilization, such as Iran or Thailand. The data center guys keep extending data centers, and also cited report forecast is ICT energy usage. By 2030, the energy utilization will keep increasing in ICT sector, and data center portion is almost more than 1/3 of our total energy usage. Let's look into what components are used most energy in the data center. As you see in this graph, more than 40% of energy is used by servers in data center. Let's look into one more level deeper. As you see in this graph, more than 60% of server power is used by CPU. So if we reduce CPU utilization, we could I think we could dramatically reduce power usage and energy usage in data center. Another trend is domain-specific architecture. I'm pretty sure you would at least hear domain-specific architecture at least once. As you may see these graphs many times. Even though the number of transistors we could integrate to microprocessor is exponentially increased, also the number of logical cores increase exponentially also, but single core performance is saturated already. So we cannot extend single processor performance anymore, even though we could integrate more transistors to SoC. Even though the processor power is saturated, the amount of data exponentially increase every year. And also as amount of data increase, we started thinking how we could how we could process data more effectively and efficiently. People started thinking we could move application or services to the data instead of moving our data from the storage to the processing servers or processing unit. As the data grows, this trend will increase because the data will attract more services application to their site. This is called data gravity. To address these things from the storage vendor's point of view and storage industry point of view, we think we need a data domain-specific architecture to address those issues. Computational storage is one of the potential solutions to address these issues. Two industry big standard groups, SNIA and NVMe, are actively working on computational storage standardization. I will discuss a little bit more in the next slide. They defined a computational storage device or computational storage drive and computational storage array and computational storage processors. What is a computational storage drive? Computational storage drive is composed of persistent storage, data storage, such as NAND flash. In addition to that, they have some computation. That can be a hardware IP accelerator, or some accelerator is running on the ARM cores. As I said, two leading standard groups are actively working on the computational storage standard. First one is SNIA. SNIA is focusing on general architecture model for computational storage. NVMe Express standard group, they are working on specific control, management, and I/O command set for computational programs. From SNIA point of view, SNIA provides some flexibility for a variety of protocols. It could run on top of NVMe or CXL in the future. But NVMe work group is mostly focused on the NVMe protocol. This is a high-level architectural diagram from the SNIA and NVMe work groups, standard groups. The SNIA defined many computational storage engines, and also they described all the components that is working on the computational storage area. The first one is computational storage function called the CSF. That is mapped to function in the that is mapped to compute namespace in NVMe standard working draft. Also, device memory in SNIA mapped to memory namespace that is defined in NVMe standard group. And finally, device storage is in the NAND flash inside the device. That is called the storage namespace in the NVMe standard spec. From now on, my colleague, Dr. Kang, will discuss one of a kind of a computational storage and evaluation result and benefit.
Thank you. So to demonstrate the benefits of computational storage devices, we developed a Postgres database scan acceleration system as an example. This diagram shows the overall architecture of our system. There are 4 software components. First, custom scan plugin parses the query, and the scan server processes the I/O and scan request. And SNIA CSC API library provides an access to Smart SSD. And finally, the NVMe device driver that implements TP4091 computation storage proposal. And on the device side, Smart SSD has a storage controller just like normal SSDs, and it additionally has a compute engine running on a separate embedded ARM processor. This ARM processor runs user-provided program written in eBPF. And in the Smart SSD, we allow the eBPF program to communicate with its internal components, such as ASIC or FPGA, by providing several built-in functions. So when a query is given from a user, Postgres first passes that to custom scan plugin. And the custom scan plugin will check and see if the query can be processed by our hardware engine. Then, it parses the query and generates a scan request for the scan solver. And then scan solver first fetches the actual data location from a file system, and then delivers the start prefetching of data into the device DRAM. And then in the meantime, it can also program the FPGA for a given query. When both informations are ready, it can start sending the scan command to the device. And on the device side, there is a eBPF program that receives the scan command and then passes to FPGA and wait for its completion and then do any post-processing work and then return. Once the scan command finishes, the scan solver can fetch the result from the device DRAM to host DRAM, and then finally send it to the custom scan plugin so you can push the data back to the PostgreSQL. So this data prefetching and scan and post-processing are all done in parallel until all the data in the table is scanned. So next. Okay. So and then this figure illustrates where the processing happens and how much data is transferred between a host and a device in the original Postgres and our system. In Postgres running on CPU, the entire raw DB pages need to be transferred from a device to a host system, and they are scanned by multiple the parallel workers to produce the result. So in order to achieve high sequential scan throughput, we need to increase the number of threads that will increase the overhead of the CPU. So our evaluation shows that the tens of threads are at least required to saturate one NVMe SSD in this case. On the other hand, our system with using Smart SSD, database DB pages are internally read by its own flash controller. So the host CPU is not utilized to load the data from the device to host system. And the scan operation is performed by in-device FPGA. So the host's role is to just send the scan command to the device. So only the final scan result need to be fetched from by a host after scan finishes. So, by doing so, we can achieve high data processing throughput and high I/O bandwidth while reducing the amount of data movements and host resource usage. This can significantly reduce the energy consumption of a system compared to the Postgres running on CPU. So this is the evaluation result. The blue bar represents Postgres running on CPU, and green bar represents our system. On the left side, the energy use chart shows that Postgres with Smart SSD uses 2 to 7 times less energy than the host system. This is because the amount of data movements are reduced and the CPU utilizations are reduced, and more energy efficient data processing in a device was possible through offloading. On the right side, the CPU utilization chart shows that Postgres with Smart SSD uses less than 1 CPU core per device. And Postgres running on CPU uses more than 80% of the CPU with 4 and 8 devices. This allows our system to scale up with the number of devices. So lastly, when you look at the end-to-end throughput chart, Postgres Smart SSD's performance increases linearly while the performance of the Postgres running on CPU is saturated after 4 devices due to the CPU contention. So in summary, the conventional data processing system architecture with high performance SSDs has been suffering from their CPU demands for computations and high bandwidth IOs for SSDs. As a result, the throughput of the system did not scale up well with the number of SSDs, and also the system consumed lots of energy. And we believe that the computational storage architecture can effectively alleviate this situation by offloading computation to low power ARM processor and hardware accelerators in SSDs. With the PostgreSQL acceleration example, we show that energy efficient computing is possible while not sacrificing performance nor scalability. So,
Okay, this is a call to action. So many of you already know that this morning, OCP FTI announced a new work stream called Computational Storage Work Stream. So I wanted to invite you guys to participate in this work stream and build an industry ecosystem together. In addition to that, as we discussed in the presentation, 2 industry-leading standards groups, SNIA and NVMe, are actively working on the computational storage stuff. So I wanted to invite you guys to this standard group and build a whole industry together. And finally, we developed E3 form factor devices, and we added computational storage features inside it. But as you know, not many servers are available in the industry to support E3 form factors. So I wanted to ask the server guys to work on the E3 form factor support also. Okay, that's it. Does anybody have any question?